give an overview here of a series of work that I've been involved with. It's been through working with the people that I'm crediting here that I've been able to move more into the field of building functional models, building models mainly on the computer that actually implement the theory of PCT. And this talk is about how we can use those models to engage a wider spectrum of scientists and maybe practitioners in the field. So I'm going to cover a few things. What are functional models? Why are they important? What do we use them for? What are our scientific motives for using them? And then separately look at what it is that the wider research community seem to want. And to see whether there's a way that we can deal with these two different goals that we have and that the wider community have. And then I'm going to cover a range of projects that I've been involved with, including robotics, modelling psychotherapeutic change, virtual reality, and the learning and prediction process. Okay, so what is a functional model? A simple way of putting it is it's the model that works, a model that actually does something rather than just sort of represents a schematic or a statistical generalization. A more detailed way of putting it would be a computational model that formalizes the hypotheses regarding the processes that occur within the individual so that the behavior of the real system can be accurately simulated. And so I'm going to, can people hear the drums in the distance?
Yeah.
Is that a good accompaniment or not? Right, let's carry on. So the idea, so there's different ways that we can test these models. We can test them qualitatively. We can run these models, visualize them and see, do what they are doing, do they resemble the way that the real system behaves? So for example, there were some elegant studies where Bill liaised with sociologists to look at the movements of groups in social gatherings and showed that they formed arcs and rings around a performer. And so there was a qualitative match there between what the model was doing and what we observe in human behavior. We can test things quantitatively. Now this can be fit to the activity itself. And so we might test it in multiple individuals, but we might not be interested in modeling those specific individuals. Or we can fit the model to each individual doing that activity and try and optimize the model to the exact way that they're doing it. And it may be that maybe some people have a stronger gain in the system, which might look like more effort, for example. And we did a study that Max Parker led where we showed that PCT models were shown to be specific to individuals, i.e. the model fit to each person doing a task was better than the average model fit of people doing that task. But it's also possible, and we've not redone this, that people might shift what they're doing during an activity. When it gets more difficult, when they learn more, they might shift the control strategy. And that's something that I don't think we've really kind of explored in depth. And one might also argue that producing these functional models is the ultimate test of a theory. You know, if you can build something that replicates the real system so closely, surely that means that the theory is a robust theory. And I've made that case in a paper with Huddy a couple of years ago. So why do we build these models and test them? We do it in one instance to show simply that living things control their perception, you know, to kind of test and demonstrate that basic tenet of PCT. We do it to show that the test of the control variable is a robust method to understand behaviour, and obviously Rick has been involved in a lot of those studies, and a lot of studies also to test models of what control variables might be using be used for different tasks and to kind of compare the functional models of different ones. And so those are important roles for functional models. Now, the question I want to say is, does that necessarily map onto the purposes that mainstream researchers have for their goals? We'll come back to that. What I've also noticed, and this is evident also in Rick's new book, is that there's much less model building that's been done of a lot of the other components of PCT. And there's some few exceptions I put in brackets there. Conflict. There's a few tests of and demonstrations of conflict in Bill Powell's book, a paper by Tim, in some elegant work by Kent. There's some demonstrations of reorganisation. There's very little out there looking at memory, looking at imagination, how PCT explains that mode in modelling awareness. There are some models of collective control, and we talked about that arcs and rings one. But when these kind of processes are modelled, there's much less emphasis, it appears, on the quantitative assessments of the match of the model to the real system. And there's reasons for that, because there's a level sometimes of complexity and uncertainty in those models. But I think it's worth reminding ourselves that there's a big gap in the quantitative testing of these components of PCT. And I think that's a challenge, because a lot of the concepts that other psychologists and people interested in human behaviour are interested in are likely to involve these components: decision-making, creativity, business management, therapeutic change, real AI, if you like. These are most likely to involve some of these other processes that we haven't got these quantitative models
I think we're losing your internet connection.
Most of our audience, they probably want to support their own. Okay, repeat myself. So many of them will be attempting to test and validate a non-PCT theory. And we talked earlier in the break about how people have got some quite kind of solidified reference points for their own work. And that's a big shift to expect them to make. Now, they might be interested in new methodologies for their own research. And I think that Rick's hopefully going to capture a real niche there, that we can help access some people on outside PCT because they see the advantages of the methodology, even if at the start they may not be fully willing to or fully conceptualize PCT itself. But I think it's quite unlikely that they are going to, as we sometimes do and often do in the papers that we write, just want to shift to PCT and realize their own theories might be incorrect or at least less accurate. So we're really kind of talking at cross purposes here, really, potentially with our audience. We're controlling different variables in a PCT sense. And I think it's a kind of a staring contest, you know, who blinks first? Do we just keep doing this and hope that people will change? Or can we take our research to a different level to try and deal with this incompatibility? And one way is to go to wider questions that scientists might be interested in that aren't necessarily the kind of focused academics. Questions that kind of capture people's attention, like, can a robot behave like a human? Can an artificial agent be mistaken for a human? How do humans learn, and can this be replicated? How can we use artificial systems to do what a human does? How do we help improve people's well-being? How can human society shift to be more sustainable? These are the kind of the big questions that people are interested in. And there's people here that are doing work that moves towards that. I'm thinking of Kent and Roger in kind of working on those wider questions. But how can we use functional models to start to move into this territory? So what ways can we tackle some of these areas? One thing we can do is to try and fit performance, not just to the tasks that we choose, but familiar experimental tasks that our colleagues are interested in. How can we use the models to try and fit societally important processes, things that people recognize as important, like psychological change in therapy, like conflict between social groups in the work that Kent works on? How can we construct models, not just as simulations where we sometimes short circuit that loop of the physical environment, but close it via the real physical world, like in robotic devices, whereby making a simulation more convincing? How can we use PCT models and compare them directly to models built from other theories, ideally working in collaboration with those other researchers? And how can we build and test these other components of the PCT model that would be necessary for proper kind of artificial intelligence, if you like, and some of the concepts that psychologists are interested in? So I'm going to talk through some of these, point you to some people that are doing some of this work already and some work in progress. So Viv Huddy has got a PCT model of a early cognitive tasks that a lot of researchers in psychology are familiar with, called the sugar factory task. That work's in progress, but the core message is that the PCT model is modeling that well compared to reinforcement learning. There's a model such as the mountain car problem, which I won't go into detail because it's work in progress. And with help from people in Manchester and with Rupert, we're developing a PCT solution to that to compare against a reinforcement learning approach. Mm. And then we have the inverted pendulum, and I'm going to share that study with you because it's published. Now, there's very little out there where you're comparing PCT models with plausible alternative models. And sometimes we cite the paper by Bill Powers and Tom Bourbon on this, but that model that they produced of a open loop cognitive system, really they constructed, it's a bit of, people could argue it's a bit of a straw man. So we really need to kind of create models that are from plausible alternative theories and make comparisons. I'm going to talk to you about some systematic work that Rupert has designed and planned with collaborators, including myself. Work on virtual reality exposure therapy. Again, it's a piece of technology that interests people, but I would argue it's actually the ideal experimental scenario because you've got this continuous measurement of input and output that's going through the system in a way that you don't have in a kind of start-stop kind of reaction time task. And then finally, it's about going against Goliath in the sense, going head on with the kind of predominant model of neuroscience and psychology, which is the predictive mind model. So I'm going to share with you the published study that I did with Rupert and Simon Watson and the really fantastic group of postgraduate researchers in Manchester. This was to create a working version of Bill Powers and Richard Kenaway's inverted pendulum, and we got support from Richard and Bruce Abbott in designing this in-house. The idea is that we had identical hardware. We also did this in simulation where the physical system was the same, but we switched the controller from a PCT one to a current one used in engineering, which is called the linear quadratic regulator. And we compared the performance of the two of them. When we did that, the PCT controller was superior in various ways. Now, we need to be kind of step back because the idea of this was to test its plausibility. But in the metrics that we had, we got improved, better accuracy from the PCT controller, greater robustness to an unpredictable disturbance, the ability to move to a new lateral position whilst keeping standing near vertical, which the competing controller didn't, And we did this in a architecture that took much less computational power, although we didn't test that formally. So what we want to do is to move on from those limitations. And the biggest limitation is that because we did manual tuning of both of these pieces of software. And so the impartial reviewer would say, well, maybe you just tuned the PCT system, you put more effort into tuning and optimizing it than the LQR system. Now, because I know the PhD student who did this, and he was working for days to tune both of them, I know that's not what happened, but it's very hard to make that claim without documenting the tuning process. And I think ideally, if the PCT system could be self-tuning through reorganisation, then that would stand, much more. Or if we had a way of verifying that tuning process. Yeah, so we could make the learning autonomous. People might critique it because we can see segues working. We can see toys called the MIPS doing the inverted pendulum. Why reinvent this system? And so its face validity is hard to then demonstrate as something where we've solved a new problem. So maybe we need to find problems that are harder, like human walking, for example. The LQR algorithm, if a psychologist was going to look at this, or a neuroscientist, they wouldn't recognize this as a manifestation of any of their theories. So there's this chasm between a theory and an engineering model that we need to deal with and address that. If we formalize that computational efficiency, I think that will be an advance. If we compare the model fit of that movement with a biological or human system, again, I think that would be an advance. So we just want to address those issues going forward, or any other groups are very willing to do that. And part of the way we plan to do that was a piece of work that Rupert initiated with a really elegant consortium of software and AI groups across Europe. And the idea was to use psychology studies and research to identify the controlled variables of human motor control and locomotion. And we would use experimental studies to identify those, motion capture dynamics, to then test their implementation within PCT utilized hardware. And we'd be able to compare by getting independent people to watch the movement of those robotic systems, how well they match biological motion. Now, this was a vast grant that Rupert put in two phases. We were unsuccessful in getting that, but all the program management for that grant and the network is in place, ready to go if we were able to get that funding. And so, I think it's important that people know about this and know that there's a potential future for this program. We're going to move now to reorganisation, the learning algorithm in PCT. Very detailed modelling within Bill's Living Control System 3. But these studies were not kind of tested quantitatively against human behaviour. And so it would be important to look at reorganisation and whether it matches the human system. The one study that Rick has described really in a lot of nice detail in his new book is a paper by Dick Robinson, where he notices that there's this trial and error variation in performance, followed by an improvement and a plateau at that improvement, which you would expect would happen when people master a new controlled variable. So our question was, can we identify this in a task for which we know the controlled variable through Rick's research, catching a fly ball, okay? And so our plan was to look for that stepped improvement as people do this task from a naive base point. So in-house, our software designer, Lee, created a computer task where you see the fielder's vision of the horizon and the ball, and you move a joystick to go in 2 dimensions on the field to try and be in the right place to catch the ball. On each trial, the ball's launched from a new pre-selected but randomly generated velocity, so that everyone gets the same sequence of trials, but they're completely unrelated to each other. And we give people no practice on this whatsoever and no instructions about how to do it, other than you need to move the joystick to get in the right place. And we record their distance from the ball every time it lands. So we're seeing if people can learn this from a novice standpoint. And we hypothesized that there would be stepped improvements in certain people doing this task. And we did this using what's called a rolling t-test, where we compare, I think it was 20 trials before and after a certain point. And we can see if there's a sudden improvement over a certain section of this continuous measurement. And then we have tested whether these improvements then actually lead to a greater correspondence with the way that the functional model does the catching task. And we hypothesized that the closer the participant gets to the ball when it lands, the closer the fit will be in their movements to the movement of the functional model. So here's an example of an individual profile where you can see these steps. So there's a lot of variation. The variation is bigger at the start, and you find that there's points where the trials improve such that the mean level goes down. You can see 2 steps in this performance, such that in those last 20 trials or so at the right hand side of the screen, there's very little variation, and most of the landing points are, you know, within a short distance of the ball. And so you only get this if you look at the individual, okay? Then what you can do is you can plot the movement of the player and the movement of the simulation trying to catch that same ball, okay? And then you can plot everybody's model fit on the x-axis, okay, against their distance from the ball on the y-axis. And this is where we get a really nice confirmation of our hypothesis. The better the person is at catching the ball, the better their fit, their model fit is. The model fit is against the real person's data. So this indicates they are using those control variables to catch the task, and the closer they control the variables that we know are involved in this task through Rick's work, the better their ability at catching it. And so Max is working on this to write this up. Okay, so now another piece of work, sorry, it's a bit longer than I planned. It involves reorganisation, but it also involves other components of PCT if we're going to have to model psychotherapeutic change, because there's hierarchies, there's awareness, which is literally the focus of reorganisation. We've also got things like the expression of a problem in language. We've got a conversation with another agent. So we've got elements that are multi-layered and multimodal, and we haven't modelled all of this for obvious reasons. So what we've focused on is being able to look at psychotherapeutic change in a very circumscribed scenario where you're controlling your level of engagement with a feared perception. Now, you could argue that that's going on in an imaginal way in all kinds of discussions about emotions and trauma and problems, but it's going on arguably in a very physical way when you control your distance from an actual thing you're afraid of, like a spider, okay? And as you know, we would conceptualize avoidance and approach to a threat in a very different way to a behaviourist. Really, they talk about avoidance and approach as though they are separately conditioned behaviours to a stimulus, as though a stimulus was a kind of a quantized perceptual experience. Whereas from a PCT perspective, that thing in the environment will have various properties, its size, its hairiness, its movement, one of which might be its distance from you, okay? And the idea is that the individual has reference points for their distance to something they're afraid of. And what I would propose is that they're in conflict over that distance. They've got a reference value to get further away from it, to keep safe, but they've also got a reference value to get closer so that they can overcome their fears, be a strong person, go into the places that they need to go into. And that what we see as approach avoidance is just the emergent actions that happen because they're in conflicts about their perceptual reference points. So how can we, and so this is a kind of really simplified rubric of that, a 3-level system, whereby at the lowest level there, they are trying to control distance, and that system is receiving conflicting signals from the level above. There's going to be a lot of systems in the middle here, but essentially you've got conflict at a middle level, but at a higher level, you've got a system that is setting those conflicting reference points. And in therapy, you need to get to that higher level so that the person can reorganize the way that they either balance or formulate those other goals so that they are no longer in the long term in conflict with themselves. So I've written a paper with Viv Huddy that came up this year in Frontiers that summarizes some of this work. Some of it was work we did quite a long time ago where our software in-house person created a bespoke PCT platform that modeled a 3-level control system in conflict. And in that early work, we found that if you focus reorganization on the top level, the one that was sending the conflicting references to the mid-level, then that reduced the error and reduced the error of the whole network. Whereas if you focus the reorganization just on one of the 2 conflicting systems, then it didn't reduce the error. So that works now. It's accessible on ResearchGate, and we've summarized it in that Frontiers article. What we didn't do in that study is do any kind of model fit to real data. And so that's the work that Mac is going to be focusing on in his PhD, whereby we're going to look at how people control their continuous distance from a spider, train the model on each individual during their early exposure, and then testing the model fit with subsequent exposure. Now, the problem we're going to have is that there are going to be changes, okay? But we're going to see if we can get some quite tight fits to people that don't make those reorganizations, but maybe show that reorganization process in the ones that have a shift through the therapy. And Matt can talk a bit more about this in a short while. Okay, the other area that I've been involved with this vast literature on the idea that the brain is a predictive machine, and it's a minefield of terminology, philosophy, and kind of pedantry. We have to work out ways of defining prediction if we're going to have to work with this group of people. Typically, what they mean by prediction is an internal, probabilistic, linear model of the environment. So that is at odds with a PCT understanding, but it's really thorny. Oh, are people still with me? It's a thorny area because this same group of people, in talking about prediction, quote homeostasis. They organize things hierarchically. They refer to PCT sometimes, and so it's a challenge to do studies that are designed to compare PCT with a predictive theory. But given that is the dominant mode of research, I think it does need to be done. So what are the differential predictions? I think they're hard to formulate because of the lack of operational definitions, but this is the way we've tried to go about it. It's often claimed by people who critique PCT and other negative feedback models that prediction of environmental systems is required, partly because the sensory feedback in the delays that come into a control system mean that it's always acting on outdated information. And so these people therefore create predictive probabilistic models to try and compensate for that. And so what Max did in his PhD was to run tracking tasks where, unlike the pseudo-random disturbances that have been used in the past, we have very predictable sinusoid disturbances, okay? And then we plot the model fit right from completely unrealistic 0 right up to half a second, which is far longer than the brain is going to take. And then the idea is to then compare these model fits to see if a PCT model can still work efficiently and map onto the way that a human does it, even when there's very predictable disturbances that you might think, well, why not just use some kind of probabilistic system to try and do the tracking here? And what Max found is that so a simple position tracking model has got a poorer fit at biologically plausible threshold of delays. So we can't kind of sit back on our laurels and just say a position control model is sufficient. However, if the model has its perception of position that is biased by its current perception of the velocity, i.e. it will perceive the target to be a bit ahead of what it is as a factor of how fast it's moving, okay? If it uses that biased perception of position to control, then it makes a much more accurate match to the human data when we optimize these models. And that doesn't require any form of probabilistic prediction or internal model of the target. All it requires is you have a model that's a bit deluded. It just perceives position in a way that doesn't reflect reality, but actually reflects future reality because it's biasing it by the future. And Max, that paper that Max has done is now in review, and we're really hoping that's going to be published very shortly. And then the other piece of work that I've done started with a master's project, and then I brought in Tauzeef, who's here today, which is great. And this is working in a predator-prey paradigm. So it's in that area, in that field, it's often proposed that prey move in what's called a protean way, which is a randomly generated way. And therefore it's thought that because predators are predictive, that if their prey moves unpredictably, they'll find it harder to catch the prey. Now, actually, when you look at the literature that's already out there, it's not actually that convincing that moving in a so-called protean way is that much more adaptive. And it depends on some quite subtle things like group size, the complexity of movement. So it's not, even the evidence out there isn't that convincing that the prey is benefiting greatly from random movement. But we wanted to do this in an experimental task where we could manipulate how predictable the movement of the prey was and see how successful the predator was at catching it, but also have a version where a human user is being the prey, okay? And if we think the human is maybe doing something different that isn't just random, that isn't just predictable, then we'll find out what that is by doing this, this version of the task. And here's the task. I'll show you this before I come back. One of the users was operating a magnet that was shifting a marker on the screen in a hexagonal kind of gameplay scenario, if you like, in 3D. And then the other user had a laser pen as the other agent, and they had to chase each other from left to right, okay? The prey either had to follow a predetermined path, and these could be very predictable ones, semi-predictable or completely random, but still heading in the right direction, in the direction towards the right-hand side, the escape area, or they could move completely free will where they wanted to, okay? And what we found is that the user-generated condition led to much larger distances between predator and prey than the predictable condition, the semi, or the random condition, okay? So there was something that human users were doing to escape the predator that was far more successful than just random movement. Now, we don't know yet exactly what that movement was, but what we might argue is that what the users were doing is dynamically controlling their distance to be as far as possible at any one point, rather than being predictable or being unpredictable. All they're doing is doing the next behaviour they need to do to maximise distance. And that would map with what Sergio Pellis and Heather Pell were modelling in their real animals. We don't know this for sure because we haven't matched it onto computational models. And so Tauzeef is building those models to see if that's what the human users were doing. Okay. So, in summary, and I'm sorry to be a bit longer than I planned, PCT researchers and mainstream researchers have largely different aims and purposes. We need to find out a high level, a way to bring those together. And I think they include just doing stuff that works, like interventions in mental health or robotics. It's about doing comparative studies, but doing our best to make our comparison a proper, plausible model, ideally with the collaboration of a competitor, and going beyond the identification of a controlled variable to actually using some of these other components of PCT that Bill kind of gave us. And, you know, I can't wait for Rick's book to come out because he covers whole new chapters on these other elements of PCT and methodologies around them. And so, but it's really hard because once you add this, everything gets more complex. As I say, it's quite hard to formulate definitive hypotheses, to compare theories. And it's quite hard to form coalitions with theorists who have their own kind of agendas. So that's where I would look for advice and suggestions about how to kind of enhance and modify or join in with what we're doing. So thank you for listening, and I'm going to stop sharing my screen now.